fine Grassmannian slices and fundamental monoptony data.
Well, thank you for the introduction, and I just want to say thank you to the organizers for the opportunity to speak and for organizing such an interesting workshop. I hope I continue that trend. I'd like to discuss some joint work with Dinakar Mataya, which appeared last year near the end of the year. But the name of the paper is roughly the title. The motivation here is coming from Coulomb branches. So that's the side of the conference I'm looking more on. But the idea is to use Coulomb branches to sort of somehow delve into some geometry of Kac-Moody on Grassmannians, whatever this means. And this is sort of following a proposal, I'd say, of Broadman, Finkelberg, and Nakajima. So my plan, I should say, so the idea is to use Coulomb branches to define the affine Grassmannian sort of, or affine Grassmannian slices in Kac-Moody type. But I did want to say one point of our work is to show that actually, even in the finite case, where we already understand the affine Grassmannian very well, most people would say, we can actually kind of learn something sort of new, namely by comparing what happens with Coulomb branches versus affine Grassmannians themselves. So, so my plan is to begin to sort of recap Coulomb branches a little bit. They were already discussed in Professor Nakajima's lecture earlier in the week. Two, I'd like by talking about this Kac-Moody case that is perhaps most exciting. Like that. So I won't recap the entire Coulomb branch story. The focus here is really on what are called quiver gauge theories, which are one of the nicest cases of this Coulomb branch story. So here we fix some quiver. Say Q. Just as an example, say some sort of oriented Dinkin diagram is usually what you should have in mind. And like in the construction of Nakajima quiver varieties, we're going to incorporate, or quiver varieties in general, we incorporate some sort of dimension vectors. So given dimension vectors, sort of V and W, well, first of all, associate some vector spaces. So I take just complex vector spaces with dimensions encoded by V and some other complex vector spaces with dimensions encoded by W. And for this Coulomb branch picture, we're supposed to associate a group and a representation of that group. So in this case, the group is the product of GLVs, whereas the representation is given by the arrows in the quiver. So I'll write the formula first, but it's much easier to remember with this picture. Let's draw. So there's a direct sum here. In the usual sort of language, the W is encoding framing. So just as an example, maybe we take this quiver. I'm going to pick some numbers. The left, right. These would be my V's, and then I have some framing. Perhaps maybe it is 0 at some nodes. So just as an example, here my W is the framing. So this is some list of numbers, 2, 7, 0. I've omitted 10, and V would be these numbers here. So physicists would say that associated to this pair G and N, or perhaps more accurately, G and the cotangent bundle of N, there's some 3D N equals to 4 quiver gauge theory. From this data. And since maybe it's more familiar to some people, just point out that this mathematically, you can see at least two things interesting from this is we can build two interesting varieties. One of them is the Higgs branch. Perhaps I'll call it M. So H for Higgs. This is the cotangent bundle of this representation, Hamiltonian reduced by the group G. In this setting with this quiver setup, this is just a Nakajima quiver variety. Very interesting varieties. The Coulomb side is what I'll be focusing on here. So here we have this Coulomb branch MC. And as Professor Nakajima explained, this is defined as the spectrum of some kind of slightly complicated ring. I'll sort of recall this a little bit more later, but this one on the right. This is the so-called BFN construction. Grassmannian Tinkelberg Nakajima. So these are the things I'll be interested in this talk. These Coulomb branches associated to all this data here. So again, fix a quiver, take V and W, build a variety out of it. Okay. Since the definition is somewhat abstract, I mean, it's some sort of convolution algebra, but the space we're taking homology of is infinite dimensional, etc. It's kind of slightly complicated, but it actually has very, very nice properties. So I don't know if some of these have been mentioned so far in this conference, so I thought maybe it'd be worth saying. So just listing a few. Of MC. So just to name a few, this thing is actually an irreducible variety. Normal even. And here I'm thinking of it over C, meaning that I'm taking complex coefficients in this homology. And in fact, the dimension is twice the rank of the group. So in this case, it's just 2 times the sum of the B's. So I don't know what that is in this example. I meant that it's not that fast, but it's something. Interestingly, this has a Poisson structure and a quantization. Again, if you watch Professor Nakajima's talk, he explained we just sort of turn on some sort of loop equivariance here, and we automatically get a quantization. Another sort of interesting thing is actually this whole construction doesn't depend on the orientation. So you may say it shouldn't be called a quiver gauge theory, it's like a graph gauge theory or something, but this is up to isomorphism. And here I should also maybe add that there are more recent works that have extended this definition to allow for sort of matter not of cotangent type. So here implicitly I'm choosing a Lagrangian inside T star n. So you could sort of maybe avoid even choosing an orientation, but for the purposes of this talk, I'm using this definition. Something I find kind of interesting, although again plays no role in this talk, is that actually you can define this over any field. Simply by taking Borel-Moore homology with coefficients in that field. So, for example, we could take C to be FQ. I couldn't resist saying this. I'll mention just so all of these properties here are proven already in the first BFN paper on Coulomb branches. It's even more general than what I'm saying because it deals with things that are not quivers. Maybe I'll just mention one more, which is that you expect that this MC always has symplectic singularities. For example, as was discussed a little in last talk. And to maybe list some modest contribution of my own, this is true for quivers with no loops and no multiple edges. That expectation seems to be panning out, although not completely general so far. One of the consequences of this, of course, is that this variety actually has finitely many symplectic leaves, which is sort of interesting.
Unoriented cycles?
Yeah. No, sorry. I mean like vertex loops, like a Jordan quiver, not allowed.
But cycles are.
Cycles are okay. Yeah. So affine type, that's okay. But no edge, no vertex loops, I guess. Thank you. Okay. That's a summary, but the main drawing point for this, what I'd like to tell you, it's a theorem of Barberman, Finkelberg, and Nakajima in their sort of second Coulomb paper. Is that if you start with a quiver of a finite ADE type, then we can say exactly what this variety is. MC is isomorphic to something I denote by W lambda mu. This lambda and mu are some decorations which depend on the framing and the dimension vectors. But this is what's known as a generalized affine Grassmannian slice. Of the same finite type. Mostly I'm going to gloss over this generalized part, but I'll sort of come back to this in a minute. Before sort of recalling a little bit of what that is, I just thought I'd maybe be worth giving an example, which is maybe the most classic example. Let's take the nilpotent cone of SLN. So in other words, just A, n by n, nilpotent matrices. Okay. Well, if you're not familiar with the story, it may not sound like something to do with the affine Grassmannian, but there's this very nice embedding, I think dualistic, which embeds this thing into the affine Grassmannian of, say, SLN. And in fact, identifies this with an affine Grassmannian slice. So if we go to this BFN theorem, then basically I need to tell you a quiver, and I need to tell you the dimension vectors on that quiver that you would put in to attain this. So, and the dimension vectors are just sort of this, actually kind of looks nice in the other way around, this kind of complete flag quiver. And the orientation doesn't matter, but so just go 1 to n. N's the only framing that we need. Very simple thing. So we're saying any nilpotent orbit. So inside here, we could take some sort of nilpotent orbit, labeled by a partition, the Jordan type, take the closure. Now these are also going to be realized in this way. Of course, the quiver is going to change. I'll give an example of that later. This has to do with the closed embeddings, which I mentioned in the title of the talk. Okay. So I thought next I would just sort of briefly recall what on earth the affine Grassmannian slice is and a little bit about why they're interesting.
This is affine Grassmannian, right?
Pardon me?
The R means affine Grassmannian.
Yes. Yes, thank you. For SLN. Or DLN if you like. Okay, so the sort of confusing thing in this topic is that affine Grassmannians appear in multiple ways. So if you recall from Professor Nakajima's talk about the construction of the Coulomb branch should somehow use the affine Grassmannian of some group. And somehow, so that's an input in this whole construction. But the claim is that the output has to do with a different affine Grassmannian for a different group, the group of the type of the quiver. So at the risk of mixing up my notation some point in the talk, what I'd like to do is take G bold, different group than the other group, this is the, say, connected. Technically, it should be adjoint type. Sort of simple group of corresponding to the quiver up there over C. So then we can look at loop groups for this group. G of O, G of K, where I'm just using this notation for our series, the Laurent series. And finally, the affine Grassmannian is the quotient. Okay. This has some very interesting in-scheme structure. So, at least set theoretically, though, one thing we can say is that this has a Cartan decomposition. So, this decomposes basically into left orbits for this group, and I denote those orbits by lambda. Explain that in a second. So here, lambda runs over a dominant co-weight of this group. Of G. And this thing is, as I said, it's a left orbit of this group, acting on some point corresponding to the co-weight. Now this is a finite dimensional smooth variety, actually. It's a natural way. But somehow the thing that will be perhaps more important here is the super varieties. These are closures of these orbits. Again, with respect to this in-scheme structure. So you can say a number of things about these. Maybe I don't need to say right now, but this is some finite dimensional singular projective variety. The dimension depends on lambda. The thing we're interested in, though, from this theorem, I remind you, is something about slices. So this is just about slices between these orbit closures. So the final piece to sort of match this notation all together is if I take two such things. If I take two dominant co-weights where one is bigger than the other in the dominance order, I guess if you don't know what that is, you could say it's just the closure order here, exactly the closure. Then, for example, ger mu will live inside ger lambda bar. And we can try to form a transverse slice to this inside here. So there's a sort of standard construction of such a thing in terms of groups. And need to be very particular, I should say it's at some particular point or something. In other words, there's some ger lambda bar here. This other one's some smaller subvariety, so maybe here's ger mu. Here's the point I'm looking at, and I want a transversal kind of like that. So here's W. Maybe the precise definition isn't so important because I've kind of told you a different definition over here. That's a reasonable definition, even though there is a easy kind of group theoretic definition, which is some sort of intersection. Okay. However, there's this word generalized, and I maybe won't define that precisely either, but I'll just say, essentially what we're going to do is remove the condition that mu is dominant. So only lambda dominant. Mu might be something else, could be anything less than lambda. Then we can kind of leave this affine-Grassmannian picture a little bit and obtain what's called a generalized slice. And as I'll explain in a second, this one is just as good almost as the original ones. So it agrees with the original definition. It actually is a transversal slice if mu is dominant, but in general, it's something else. Well, and again, what's the definition? Well, you could say, take the Coulomb branch for that quiver data. So the final piece maybe which I could write down here is, what are lambda and mu? So remember that here we had some dimension vectors v and w, and just as in Nakajima's work, we associate two, well, co-weights in this case. Lambda is encoded by the framing. These are fundamental co-weights of the group. That's why I mentioned adjoint type, but that doesn't really matter. And the V's are encoding sort of how far below lambda we are. So the fact that this is positive is exactly telling us that lambda is greater or equal to mu. We're not necessarily encoding though that mu is dominant. So lambda certainly is, mu is less than lambda, but that's it. Okay. Any questions so far? I think I'll leave that up. Okay, so the main reason for this whole picture well, first of all, you could say all those properties about Coulomb branches I listed before hold for these slices. So they're finite dimensional affine varieties. They have Poisson structures, etc. But there's a more interesting one, which is that these are some sort of geometric incarnations of weight spaces. So maybe I'll just quickly summarize that. Here's some version of geometric Satake, which is not going to be stated as an equivalence of categories because I'm not going to use a category, but rather I'm going to tell you how to build a representation. But still, let me just recall that this is a Lustig, Ginsburg, Merkowitz, Valonen. Maybe in the form that I'm about to state, I should also add Krylov. Namely, what we can do is take these varieties W, lambda, mu. It turns out they have some interesting Forest actions. So there's an interesting C star action, and we can take the attracting set. So this is some attracting set. So C star. We take the top Borel homology of this. And the claim is that this is a weight space for the Langlands dual group. So to get the whole representation, we should take all these different mu's together. So the claim is that this is one mu at a time isomorphic to some weight spaces of a representation V lambda. This is a module over, make sure to do this bold. Again, we took an ADE group for our ADE quiver. We take the Langlands dual. This is the irreducible module of highest weight lambda. That's why it's important lambda is dominant co-weight. Dominant co-weights are like weights for the Langlands dual. So, and again, you can erase the direct sum and just say, well, each one of these is actually isomorphic to that. But in this version, notice that there's also a group action. That's all we're saying. There's some natural group action here, or Lie algebra.
Is it easy to state a Q version in this?
A Q version?
Yeah.
Like a homology or something?
Well, I don't know, to get the representation of the quantum group. No,
I don't know. That's a good question. Okay, then it's not sure. Sorry.
K theory.
Somehow sitting in the equivariant K theory, yeah.
I would have thought. Okay. thought you would just say yes, of course.
Yes, of course. That's easy. Okay. So I'd like to turn them to the, I think there's a fire alarm coming soon if I'm not mistaken. But, yeah. I didn't quite time that right. Okay, the thing I'd like to turn to is this, one of the central topics in this idea is that we were studying closed embeddings. I don't need this for this Satake story, but it's an interesting thing. The idea here is instead of taking two co-weights, mu and lambda, I'll take something in the middle. The all dominant. Then what we can do is, well, we can take all of the associated Schubert varieties. And maybe I'll put closures on the bigger two. I'll keep running.
You're supposed to have your summary.
I know I was supposed to have a summary. Sorry, it was a good suggestion. I chickened out. Okay. The claim is that just as the Schubert varieties embed into each other, so do their transversal slices. And again, I didn't exactly recall the construction, but it's quite natural from that construction that you just have a subset like this. So the transverse slice between sort of mu and nu will sit inside the one from mu to lambda, some sort of embeddings. These are actually closed Poisson embeddings. And in fact, you can erase this, all of them being dominant, talk about generalized slices. Then I only need lambda and mu to be dominant. I guess I should erase it. So the claim is generalized slices have close embeddings. And that from the affine Grassmannian point of view, this is very, very natural. The idea, or sort of the starting point of this work of ours, was what happens if you use this BFN result, replace both of these with Coulomb branches. On the one side, we have some Coulomb branch. On the other side, we have some other Coulomb branch. So the data will be different. So here there's some quiver data. Here there's some other quiver data. Again, from the affine Grassmannian point of view, it's very natural you have closed embeddings. They're just subsets. Okay, the question is sort of what's this? How do you relate Coulomb branches together? You know, without ever mentioning the top. That's kind of what we're interested in. Okay, that's the story. Maybe one thing I'll just point out, that's not so important, but I may come back a little bit later. The quiver data here is going to be different. But you should think one thing is that the quiver data, these gauge nodes here are going to be bigger than those ones. Let me illustrate this with a picture. So in some sense, you're kind of starting with a Coulomb branch for some quiver. And then you're kind of replacing or reducing to a smaller quiver. But however, the dimensions change. So here's an example. I mentioned before that nilpotent orbit closures in type A are all Coulomb branches. So remember, nilpotent orbits are labeled by some partition. Let's look at 3, 1, 1. I think I put it below before. Anyway, in other words, matrices whose Jordan type is 3, 1, 1 that are nilpotent. So this sits inside the nilpotent cone of SL5. They're going to be 5 by 5 matrices. You can work out what are the quivers corresponding to these. Well, here it's something like, hopefully I did this correctly. 1, 2, 2, 2. And the framing is 2, 1. This one over here, I already mentioned. This is always going to be this sort of complete flag type quiver. Here, I'll just flip the arrows around for fun. Like that. So somehow we're supposed to relate this theory and that theory. I'll mention that there's I told myself I wouldn't get too tangential on symplectic duality, but if you look at quiver varieties, there's an analogous statement to what we're asking, which is when is this quiver variety for this, a transversal slice in that one? Some duality between slices and leaves. So anyway. But from the Coulomb point of view, it's sort of not so obvious how you take that algebra and turn it into this one, in my opinion. Let me just hit that what I mean. So again, you have a picture like this. The coordinate rings of these two varieties are convolution algebras. So I'd start with the bigger one. And what we're asking for essentially is a surjective map onto this one. And I mean, oh, sorry.
I'm sorry, on the dual side, would it happen that framing dimensions would be the same?
Pardon me? Yes, I think everything is the same. Yeah.
I mean, on the dual, on the symplectic dual quiver side,
Right.
the framings would be the same, but the circles would be different. Is that,
Yes.
is it the right?
Sounds reasonable. Yeah, I'm not sure, but
Right, on the dual side, you're keeping lambda fixed and comparing mu and mu.
yes, right. Thank you. So I was going to mention, you might hope that to produce this geometrically. We're dealing with topological sorts of things. Maybe there's some way of taking a correspondence between this and this, something like that. But I just wanted to point out that this isn't what we do, and we don't know how to do this. It can't really be too naive. It can't be anything too straightforward. And somehow the reason is that, or it's a heuristic maybe, but if there is some very easy geometric way to build a map from here to here, and I mean, again, in terms of these triple spaces, then it would quantize, probably. I mean, just put equivariance in. That's the idea. The idea, though, is that I mean, these don't always quantize. Well, with maybe a caveat, without, you can typically do something, but you need to be very careful about deformation parameters. Again, in Professor Nakatima's talk, he was talking about flavor symmetry, incorporating that on both sides. That somehow, if you finely tune it on one side and the other, maybe it will work without sort of like tuning the deformation parameters. Yes.
What if you consider flavor deformation, and then you just don't set parameters to anything?
Right. Then I don't think it will work. I mean, somehow we know some examples in type A where you take the universal deformation of the smaller guy, and you can show that you can extend that to some deformation here. But I think there are examples where that's just not possible. Somehow both of them need to be constrained. So
The generic parameters, the left-hand algebra would be simple and it wouldn't have any quotient.
oh, that's not a good reason. There's a simple example though, which is just take the nilpotent cone of SL2. I mean, the usual actual cone. Take the cone point. And if you run through this whole Coulomb range story, the quantization you get of the nilpotent cone is like U of SL2 mod the central character where there's only one highest weight. I forget what that one's called. But in particular, this does not have this for this particular choice does not have any map to C. Right. So I mean it would sort of quantize to a map to C. This is a little sketchy, but
With as bimodules. So
maybe.
yeah.
Maybe. Good point. Anyway, as I said, it's a heuristic, so maybe there's something you can do. Rather, we take a different approach. which is use what are called, or what we call fundamental monopole operators. This is sort of like the more algebraic side of this Coulomb story. So I'd like to talk about that for a few minutes. Essentially, the idea though is that Coulomb branches have certain natural functions you can write down. Called monopole operators, which are inspired by physics, but can be written down mathematically in the Coulomb branch framework. So for this, I can write down maybe a little bit more. So the space that we take homology of in these setups are, and maybe I'll refer to Professor Nakajima's talk for a little bit more detail, but the point was somehow it lives inside some vector bundle. You sort of take an induced bundle, loop group of G, and you take loops into N. And the point is this lives over the affine Grassmannian of G. As I said, this is where things get a little confusing. This is not the bold G. There's two different G's here. Please keep in mind. And so we have in particular a map like this. And what we can start to do is take super varieties here. So there are super varieties appearing in the talk already, ADA type, but here they're for this group. And this G is for a quiver anyway, just a product of GL B's. So it's a very easy affine Grassmannian, relatively speaking. Easy, I mean, it's very nice. The idea is to take certain nice loci in here and take their preimages. So what we can do is, for example, we can take subspaces. We take the evoke around homology, but what we do is we take this preimages in R of certain nice things. For example, a Schubert variety. But we can do better. We should not just take any super variety because they're singular. It's hard to compute things. You can do the sort of simplest thing, which is, I should say, sorry, roughly speaking, classes here are what are called monopole operators. So maybe there's some ambiguity about exactly which ones are which or something. So let's just be concrete. In this quiver situation, we're dealing with a bunch of GLPs. So just to allow myself some notation, what we can do is choose a tuple. This isn't exactly a dimension vector, but it's a bunch of integers again, where each of these is between 0 and VI. These are the dimension vectors of our quiver. And what we can do is associate a co-weight gamma for GL for this group G. So what we do is at every single node, where we have a product of general linear groups, the co-characters of those are just tuples of integers. So I'll just tell you, you take a fundamental. So here I have sort of MI elements, and I'm thinking of this as a co-weight for this individual summon is a co-weight for GLVI. So we can sort of naturally interpret their sum as a co-weight for the product. And the upshot is that this is a good choice because this is minuscule, which means again that the closure of this Schubert variety is the same as not taking a closure. It's already closed. And in this case, it's very nice. It's a product of Grassmannians. Okay, so we're taking Grassmannians of like MI planes and VI. And that's where this bound comes from. So we're just allowing ourselves Grassmannians in individual pieces. Okay, and one more thing, I can write them down. There's a sort of long equation to write. Maybe I can write it here. So in this case, if I take this choice, Again, don't need the bar. But it actually turns out if you take the preimage of this particular choice of locus, so this is living in here. It turns out that over top of this, it's actually a vector bundle. And so there's like a isomorphism. So you don't need to deal with all this infinite dimensional stuff anymore. You have this variety. And as we see, that variety is a product of finite dimensional Grassmannians. This is just a tensor product over I of some sort of like GLVI hypervariant cohomology or homology, I'm sorry, of a Grassmannian. Further, you can identify this with some sort of tensor product of like partially symmetric polynomials. So maybe the notation doesn't matter, but just to point out, it's nothing complicated. You take polynomials in VI, many variables, and then you take like product of symmetric groups. Nice VI. Okay. And the idea is now you have a way of producing elements of the Coulomb branch algebra. So we start with some polynomial. So F is an element here. Apologize for the notation. What we'll do is sort of run backwards through this isomorphism. We get some element here, and we can think of that as a function on the Coulomb branch. So we've taken to denoting this by M plus F for monopole operator. Plus, because you can run the whole same story, sort of putting minuses here. That won't be dominant, but you can shift it to be dominant around. And somehow the idea is that these are the simplest operators you can write down because of all this smoothness, non-isomorphism, etc. But it turns out that for quivers, you can show that these generate the ring. Oh, sorry, these are what I call fundamental monopole operators. I could have written that. The ones from the title. You might call them minuscule monopole operators because gamma is minuscule, but here we call them fundamental because these are all fundamental. So these, we take to abbreviating it FMOs, fundamental monopole operators, but they all look like that. They generate the coordinate ring of the Coulomb. But this is completely intrinsic to quivers somehow. So for any quiver, you can have loops here. Yes. Oh yes, yeah, they're dressed. Sorry, the F is the dressing. Yeah.
Generate over at the homology of a point.
Yeah, I mean, I guess if you like, you could say, what if I take the tuple that's all zeros, right? Then I have a product of Grassmannians of zero planes, and so you have a point. So they're kind of part of it, but that's a great question. Yeah. Yeah, I thought I'd gloss over this. So you're right, though. There's some natural functions here, which is like the integral system. Very nice. Okay. And so the point is we have these natural functions, they generate the ring. We can try to use them to probe things, properties of the Coulomb branch. And so this comes to our first theorem. So we look at one of these closed embeddings that I mentioned before. So maybe I'll briefly write the picture again. And you have a affine Grassmannian slice. You have a larger affine Grassmannian slice. This one is a Coulomb branch. Prime. And here, well, we know that there's some sort of map between them. The point is somehow, seriously, these fundamental monopole operators are restrict to the same things. So they restrict very simply. And sense, which is maybe tedious to write out, but. Well, when I'm teaching, I drop the eraser at least once every class. It's like a universal rule. So I'm glad to see it's still. So, okay, we have the coordinate ring of this larger algebra, of this larger Coulomb branch. It has some of these elements that we just discussed. These stressed fundamental multiple operators. I can restrict them under this map. And the claim is that either they restrict to exactly the same thing with the same data. Other than that, I'll explain this, but you have to sort of tweak that function, but it's nothing complicated, or they restrict to 0. That's it. Everything stays the same. And the only real distinction here is, as I mentioned, here you have some gauge groups, some quiver data V and W. Here you have some other data. These ones are going to be smaller. And if you just go back to this picture of Grassmannians, you're going to start comparing things like a Grassmannian of MI planes in VI prime. But VI prime is smaller than VI. So it's possible that this will be too big and that this is kind of empty. I mean, in other words, it's possible we're looking for like VI planes in VI prime. So it's just nothing. And that's what's controlling this. So essentially, if M is too big, so if it's small enough that it makes sense to talk about Grassmannians, you're fine, everything works. Otherwise, it goes to 0. That's somehow. Okay. Maybe I can make a couple comments before ending with moving to this Kac-Moody setting. So just a couple of remarks. I haven't gone into it, but one of the nicest things about these particular elements is because we're dealing with smooth varieties, we're taking homology on this. You can use the localization theorem to write things very explicitly. So usually you might work if you open, for example, the papers of BFM, you'll see some formulas for what these look like localized. And that's normally how you might deal with them. I won't write them out. But the problem is when you have one of these closed embeddings, I could localize and write everything very explicitly on the larger one. But it turns out the denominators will vanish under this inclusion. The denominators vanish. When restricted to the smaller variety. MC prime inside MC. So you can't really use localization, at least not right away, to prove this sort of statement that I said. We have to kind of work around this a little bit. So the workaround, which I won't entirely explain, but you can see our paper is to do a related calculation for something called the Zastava space. Maybe in a word, Zastava spaces are closely related to this whole story. They're kind of like a related variety, can also be built using the Coulomb branch construction, but they don't have this issue anymore. The denominators do not vanish, or rather you can tweak it so that they don't fight. The other thing I wanted to say is I'm telling you that this, we have these nice varieties, Coulomb branches. The Coulomb branches have nice functions, these things. And then I was saying earlier that you recover many interesting familiar varieties this way, like the nilpotent cone. So for example, maybe we're talking about the nilpotent cone and we're talking about these multiple operators. We don't know what they are. So another comment. Two things. One, we don't know the relations. Satisfied by these operators, by these elements. Simply that they generate. And two, we don't know what they are. We don't know explicitly. Maybe let me, yeah. What they are in examples. I mean, we know some of them. So just as an example, for example, I mentioned the nilpotent cone. Well, we have lots of very nice functions on the nilpotent cone, like matrix coefficients. I'm saying that here you have some a little bit strange looking functions labeled this way. And in general, I don't know what functions they are here. So, question, does anyone know what they are?
You take two Schubert cells, one codimension one and another.
Yes.
Usually you can write explicit function cutting it out.
Right.
So it must be this function that.
Here the problem is the Schubert varieties are not, these are not Iwahori, sorry. These are Iwahori overclosures, but they're not all of the Iwahori overclosures. We're only looking at spherical Schubert varieties. So actually they're not codimension one. Well, no, I don't think they're ever codimension two. In fact, everything is sort of Poisson and symplectic, so you can only see differences of two. So the functions cutting them out is actually a little subtle, but it's an interesting question.
On Zastava side, maybe.
Maybe, yes. I should say, actually, yes, on the Zastava side, we know you can say what the ideal of this is, for example, in terms of these operators.
Yeah, but I know how to calculate.
That's good. Yeah, I know how to write a rational expression for this, but I don't know what it is. Okay, we could talk a lot about this. So I guess in the final few minutes, I don't know when we started.
Yeah, I think that you have more like 10 minutes.
Okay, I know it's lunchtime. I don't want to keep everyone. But let me say a few things about the Kac-Moody case. Maybe one final comment. Some other functions you have here are like minors. You know, take a submatrix and take the determinant. These are all monopole operators. So all the matrix coefficients are monopole operators, all the minors are monopole operators, but there are even more monopole operators, and that's what we don't know what they are. Anyway, okay. So I'd say, like, you know, there's a general pattern here. If we have a quiver with no loops, again, I mean vertex loops, so no stuff like this, then you could think of this as the Dinkin diagram or oriented Dinkin diagram of some symmetric Kac-Moody algebra. Right. And you know, there are various definitions of a group associated to this. So let's say we pick the right one. Then you can try to make sense. I mean, I don't know of any significant progress, but what is GER of this? I think it's sort of a very difficult question. Maybe set theoretically, there's some guess, you take loops, but a scheme, etc. I won't try to speculate, but there's a proposal that goes back to Brabham and Finkelberg, which is that you should not try to define that, you should just define the slicing. As we saw, maybe you don't get a full geometric Satake equivalence of categories like the usual one, but maybe you can recover the one I mentioned. Namely, take the top homology of these things and build a representation out of it. So, in some version of Satake, hopefully. Again, the one I alluded to earlier. And well, I hope it's maybe obvious what I'm about to say, but thanks to this cool construction, we can simply use that as a definition. So this is our proposal, which I think it's safe to attribute to Rodman, Finkelberg, and Nakajima again, which is just define this affine Grassmannian slice, whatever that's supposed to be, as, I mean, again, this definition as the Coulomb ring. So again, I'm choosing co-weights of my group, my Kac-Moody group. I'm converting them into quiver data, applying this whole machinery and making some space out of it.
The Coulomb bunch of Kac-Moody group of
Yes. Sorry, no, the group here is still finite. It's still just the one built out of a quiver. So, maybe we're doing affine type A or something. You'll have some picture. You'll have a GLN, something.
Why should it gives a right answer?
That's a good question. The claim is that it's a reasonable answer. Here's one evidence. I think the most convincing so far is work with Nakajima. Says that in affine type A, this is reasonable. You can do what I mentioned before. You take a direct sum over mu. I'll just phrase it the way I used before. So you take some sort of attracting sets. You take their top or more homology, and the claim is that this is again a representation. And with the action of the affine Lie algebra. Now this proof uses both varieties. So it's very, very nice, but maybe a little special to type A so far, not known outside. But yes, this is some evidence that it's reasonable. So the final thing I'd like to say is, well, in fact, these things embed. I wanted to say anything else? No, not yet. Okay. So here's the
Before it was.
yes. Why? It's sort of like natural generalization ADE would be symmetric Kac-Moody.
Oh, that's okay. So yeah.
Yeah, not all Kac-Moody. Okay, so for general type, I mean symmetric and choose data as before. So that's to say mu, nu, lambda, where these are dominant. Then there exists a closed embedding. Also closed. And it still has exactly the same property, which is how we came up with it, that these monopole operators restrict in some very easy way. Same thing as before. The only difference is there's an extra condition. If I'll explain this briefly and then stop, but if nu is what's called good for lambda, so there's some additional complication coming in. But otherwise, the story is more or less the same. So, and in particular, in finite type, we recover the usual maps, but we build them without using the affine Grassmannian itself. Okay, a couple minutes. So what is good? This is terminology coming from physics, not so surprisingly. And yes.
I think you just rubbed off. Sorry.
Oh, sorry. Sorry, I should have erased
Does
that.
this map give you any? Well, it seems not. But is there any map on homology then coming from these?
Oh, well, I mean, in a sort of indirect way, yes. Yeah, in fact, we do write down, I won't maybe talk about the proof, or we can talk about it after, but we sort of build a map in steps. That map actually maps into some localization of a ring, and then we use the monopole operators to check that it's regular. So it's semi-geometric construction. It is in terms of homologies of things. Not quite as direct as you might hope. So here. So there's a notion of good, bad, and ugly theories. Which is due, I think, to Guido and Witten, or at least that's where I've heard of this. And here, what we need to do is, here we look at a different slice. So I'm dealing with these two, but actually you should take another one. Lambda and nu. So lambda and nu are both dominant and they're less than each other. And this is also a Coulomb branch. What we need is this to be good. There's not much time to try to say what that means, but it means that it's conical, basically. And the cone point is Poisson. And final maybe sentence I'll say is just in finite type, sort of a lemma. In finite type, you don't need to deal with this. You're always good. And the second thing you can say is that in affine types, any affine type, good corresponds to level greater than or equal to 2. The level of lambda, which is the same as the level of everything, greater or equal to 2. But level 1 and level 0 are slightly problematic somehow. Anyway, I'll stop there. Thanks for listening and sorry for going on.